Hello, so welcome to CSE 564, Visualization, Visual Analytics. Today we're going to talk about scientific visualization and following up on this lecture on volume visualization from last time. So this shows this here. So last time we spoke about volume rendering, how you can render volumes from 3D arrays of voxels or densities and directly with ray tracing. Today I'm going to talk a little bit more about volume rendering, but now we're trying to reconstruct a geometric surface from that volume. Okay, and then we can render this like these polygons. This is a polygonal surface that is closed and watertight, and we can try to render that surface with polygonal rendering hardware, like just any other geometric model, like for CAD, CAM, and things like this. So we learned about if you don't have a lot of polygons, it looks very coarse, then it gets a little finer and even finer, and when you shade it, it looks like the real object almost, So, but it's empty, once you created the surface out of polygons, when you drill in, there's nothing there, right? In volume rendering with ray casting, on the other hand, there was actually something behind, right? Because you never really lost the underlying volume. So how do you create this kind of surface? Because remember, in volume rendering, you create the surface on the fly, right? Because there could be many, many surfaces and you have to decide which one by using what's called isosurfacing. So there is an algorithm developed in the 1990s that's called marching cubes that will accomplish that. It will basically create a surface from individual cells, and then it finds the polygons in each of these cells, and then you can just sort of like add them together and it becomes the surface, So marching cubes it's called because you go cube by cube and create the polygons that make up this cube, one by one, or in parallel. You can do this in parallel too. So how does this work? Basically, when you go down here on the bottom left, you'll see each cell is basically made out of 8 voxels, or 8 samples. And those samples could either be, the value of these samples could either be a greater than the ISO value or less than, or equal or less than the ISO value. Okay, and you're gonna put the surface to separate the voxels that are below the ISO surface from those that are above, right? Where the value is below the ISO value and the ones above, right? In this case, only one sample had a value that was greater than the ISO value, and all the other ones were below. So if you imagine a surface between those, essentially this can be represented by a single polygon or by a single triangle like this. That basically clearly separates the inside sample from all the outside samples. And there's also the reverse case, of course, here, where all these values here were inside and the other one is outside. So it's exactly the same case, just flipped around, right? And if you think about it, there really are 256 possible configurations. Like each voxel each sample could be turned on or turned off. Like each value could be below the ISO value or above, or equal or above. And then basically there are 256 to the power of 8 cases. Okay, turns out these 256 possible configurations there are really only 15 base cases. They're not, and the other ones are just symmetrical equivalents, or inside out, right? For example, this is the empty cell, and the opposite case is when everyone is full, right? When all the voxels are basically above the ISO value, right? So it's the opposite case, but still there's no polygon. Here the same end too, on the next one here, this one is above and the other ones are below, but the other way around could also be true. All the other ones are below and upward. So it's about maps to the same case. And likewise here, this voxel could be anywhere, right? It could be up here, could be up here, could be up here. It'll just be a polygon, just be in a different place, but still only be one sort of configuration of polygons. And likewise these ones, right? So this is the case with kind of a blade. Here, there's an isosurfaces on it. There's basically 2 objects. There's one on the left lower corner, one on the left upper corner, but this could also be shifted over, right? This could be here or here or here, right? There could be many ways, and they all be the same base case basically. This is another configuration, a third, fourth one, and so on, right? So these are basically 254. These are these 15 base cases. So the next thing is, The next thing is to figure out where exactly does this polygon fall on each of these edges, right? So there's many choices, right? It can each of these vertices of the polygon can shift from left to right. So, but what is the exact placement? And the exact placement really is determined by this actual value and by the actual value on the other side of the edge, right? And then here's another edge here, depends on this value and this value, and this placement here depends on this value and this value. And the closer this value is to the ISO value, right, then probably the vertex will be closer to it. When it's really high, right, it'll be maybe further out. So we'll basically determine this by linear interpolation. So we'll find out where on this line, given this value here and given this value here, these are actual values, right? Given this value here, is where, linearly speaking, is this ISO surface, right? Where is the ISO value exactly, right? This is, you know, if the ISO value is 5 and this is 10 and this is 0, then this surface will go right in the middle because 5 is in the middle if the ISO value is 5. So essentially we're trying to solve this equation here by linear interpolation. So the voxel 1 is here, gets weighted by 1 minus u, and this voxel 2 gets weighted by u, when assuming that this length here is 1. Okay, and then we'll solve for u because we want to know where it falls. So we're going to solve for u, which is essentially v1 minus ISO over v1 minus v2, and that will find u. So we'll do this for every edge. Whenever we have a configuration with where a vertex falls on an edge, we'll figure out what this u is, right? We'll figure it out here. We'll figure out here. Anytime a polygon crosses an edge, we'll figure out the placement using this equation here. We can also find we can use then this u to figure out what the color of that vertex should be, using this color and this color that we maybe pre-shaded, or the normal even, right? If we establish normals by central differencing. All of these things can be then found once we have this particular value u, which is determined by the isosurface. Okay, and then basically by magic, basically, you know, they are connected, right? These polygons are connected because the next cell on the left-hand side, let's imagine there's another cell on the left-hand side, will have the same, will also have a polygon, right? Will also have a value here that is above the ISO value here and the one below, right? So the next cell will also have a polygon with a vertex like this. It may have a different configuration, but the same placement, right? So basically this is how you see that these things are going to be connecting together, right, and create the object one by one, right? There's an issue with holes that has been, you know, that there's some very ill-placed, there's some ill cases where this main is not fulfilled, and later on people found out, maybe a year or two later, people found out that there may be holes, and there is some special cases that have been created that eliminate those holes. But let's leave this aside for now, right? What I usually do, I just make 256 cases directly. I don't go to the symmetry. There's enough usually. Back then there was not a lot of memory that you had. You had to really limit the lookup tables. Nowadays there's a lot more memory. You can just spell out those 256 cases one by one, so you don't have to translate them into base cases. And then you can, you know, you can solve these problems a little more. You know, it makes it also easier to compute. But anyway, so let's go look at the video, right? So you have this video here. This is like a particular configuration, and then you'll say, okay, let's increase the ISO value, you know, and then, you know, they'll basically see, I'm decreasing the ISO value, right? Decreasing the ISO value. Now I'm gonna get different surfaces. So now I'm increasing it again, get different surfaces. So this goes really, you know, see how these things are connected, right? So this is the real-time marching cubes. You know, so this is like, and each of, now you can see there's a coarse, right? You can see how coarse it is because there's like these cells are actually visible. You know, there's not that many cells here, but the surface just changes by changing the ISO value. It's also a time varying volume, I think, maybe not. So you get the idea, right? So basically, find polygon for each cell, connect the polygons, and just render them. Polygonal rendering is like you can just render, you know, you use the Z-buffer algorithm that you learned about last time to figure out which polygon is visible and which one is not visible. You can actually parallel render those polygons in any order, right? They will just appear in the right order because you're using the occlusion culling with Z buffer. You know, you will see the object like this. You will only see the visible surface and not the invisible ones. Okay, so next let's move on to like where these data come from. Okay, so we've talked about, you know, we've completed the lecture on volume rendering. First I showed you ray tracing last time, and now I showed you marching cubes that creates the geometric object. So now I want to ask you what this is. Okay, what is this actually? You know, it looks like a closet kind of, you know, there's the word Titan on it, and it's very interesting pictures mapped. You know, so this is actually a supercomputer in Oak Ridge National Lab called Titan. And this one time it was one of the fastest supercomputers in the world. And basically in each of these racks are many CPUs and boards and GPUs and so on. And what you see outside printed here are these different kind of simulations that this supercomputer is modeled and then visualized with techniques I'm going to show you now in this lecture. So, you know, this particular supercomputer could do 10 petaflops. It's, you know, released, it was in 2012, where it was one of the fastest computers. And a petaflop basically is 10 to the power 15 floating point ops per second, floating point operations per second. This, you know, so you need this kind of horsepower if you have these demanding applications. I'm going to show you some of them in the next slide. So, you know, basically there were 18,000 odd AMD Opteron processors, 16 core CPUs. They're also, you know, close to 20,000 NVIDIA Tesla K20X GPUs. This was back then, 2012. This was sort of top of the line hardware. Okay, and nowadays it gets even faster. You know, there was like the supercomputer race is very demanding. You know, with Japan and China in the game, and some European supercomputers. But now I'm happy to report that, you know, 2018, the US has captured the crown of supercomputing again with the Summit supercomputer, which is also the Oak Ridge National Lab. It was '1 in 2018, still is, I think. And this could do 200 petaflops. Remember, the other one could do 10. This one can do 200, like, you know, 20 times more. And you know, is twice the top speed of the Taihu Light in China, which was the previous #1. And this one has 4,600 compute servers, and each of these has two 22-core IBM Power 9 processors and 6 NVIDIA Tesla V100 GPUs. Okay, so it's substantially faster, right? So what does it actually do? Okay, so it's basically computing and computing. You know, that's what it's made, and that's what it does. Okay, produce a lot of data. So some examples here. So S3D, that it models the molecular physics of combustion. So you can basically use this to optimize diesel and biofuel engines, right? So this is very important, right? So instead of having to build all these different engines to see, you know, if they're more efficient or not, you can model them. But you can model the underlying physics of combustion, which is, you know, which can really speed up development and make things even feasible, right? Sometimes you can't even measure things if you build the actual physical model, right? This way you can actually understand it. You actually understand. Nowadays there's a lot of effort placed on battery development, okay, simulating how the molecular process works in batteries. You know, there's also a lot of research on this. Another one is de novo, simulates the nuclear reactions with the aim of improving the efficiency in reducing waste of nuclear reactors and other things. So nowadays you don't have to explode nuclear bombs, or you don't have to build nuclear reactors to figure out how safe they are or how efficient they are. You can just simulate that on a supercomputer, right? Which also, you know, requires a lot of resolution, like to make sure that you get to capture every little, you know, aspect of it. So you need a lot of resolution. So you need a lot of cells, so the data sets gets massive. So you need these massive number of CPUs to actually, you know, model this propagation of energy and so on with these finite element and so on, finite differencing operations. Another one is LSMS, interactions between electrons and atoms in magnetic materials. And that's another one. Bonsai is that simulates the Milky Way galaxy on a star-by-star basis. Tries to explain also the Big Bang and things like this, you know. So you can see there's a lot of different areas, scientific areas that all get addressed here. Non-equilibrium radiation diffusion. That is supernova with potential application, laser fusion, fluid dynamics, medical imaging, nuclear reactors, energy storage and combustion, right? So, there's a lot of things there, right? So as you can see, there's many different ways these supercomputers can be harnessed and put to use, and this massive compute power is needed because the real world is also massive and parallel, right? So to simulate these real world processes, you need an equally massive parallel system to make sure you can actually do this in a feasible time. But you can also do this on your iPhone or Android, but it'll take a lot of years or more than to compute that. So this way you can sort of simulate it almost at the speed it actually appears, right? And you can try a lot of different things and can even steer it, right? So that's basically what this hardware will do. Okay, so expensive hardware, and you need to file an application if you want to run something on it, because it's there's not a lot of them out there, but gives it is. So what does it output? Okay, basically numbers. You get lots of numbers. Okay, that's really all you get, right? There's no, you've seen these pictures, but those pictures don't come out, right? You get numbers, and then you have to take these numbers and turn them into pictures. Okay, so so you need this. You basically, this Titan I/O subsystem can push around 240 gigabyte of data, and 240 gigabyte of data, and that's a lot to visualize, right? So 240 gigabyte of data per second. It's a lot to visualize in real time, because you want to see it and see, maybe the simulation didn't go well. You want to detect that, right, and then see what happens. So for example, here's one example, the Q continuum simulation for cosmology. Okay, so so giga year, right? We're talking about long time spans. Understand, these kind of simulations, because they went on for millions of years, right? So you have to sort of see this. So to you, except for a non-expert, this may look not very interesting. You can sort of see how it was dense in the beginning. It got more sparse. That's kind of like the Big Bang, right? It was dense and it sort of expanded out, right? So, but where it expands and how it expands is very interesting to know, right? So this may not look very interesting to you, but or very, you don't really know the fine nuances of this, but an expert will get a lot of insight out of these pictures, So okay, so more examples. This is a nuclear quantum molecular modeling. Is a model. Okay, then there's some structures here, a tubular for fluid and field. So see how the field goes, and there's another molecular or fluid model. Okay, so these are just some pictures I want to show you without going into detail how they were generated. Just sort of see the variety of things that are coming up there, and I'm going to give you some methods now how to actually create these kind of pictures. Some more examples. Surface rendering with VTK. So VTK is the visualization toolkit, which is a library created by scientists and commercial efforts by visualization experts to give scientists a library by which they can create visualizations. Okay, VTK is very famous, visualization toolkit, and here volume rendering will also be done by VTK. So it has these hotspots here. So very nice. Of course, they look very pretty, but they're also meaningful. So visualization is a nice field to be in, right? You create beautiful pictures that help people understand the world, right? Other than art, where you just make a beautiful picture for entertainment, but here it's actually a beautiful picture where people can actually understand things better that they didn't understand before. So where to visualize all this? Okay, so here I want to show you some environments that are used where people usually meet, scientists meet, and look at the data together, because oftentimes you want to do this in a collaborative environment, because someone may have an idea and someone else may have another idea. They talk about it and then sort of start exploring the data. So one of them is this display wall. Okay, so display wall essentially is a very large screen, and there's these where you can fit multiple pictures on it. Okay, very high resolution often, and then you can basically, it's you see this in a flight simulation and in other national security applications, so on, command centers, even AT&T has one for the network, to see the network and so on, right? But these are like basically each of these is a display, and then they're tiled together on this sort of large display. Kind of looks like Times Square nowadays, but these are more high resolution, right? Because you get closer to them. In Times Square, displays are very far, so when you walk up to them, you can see individual pixels. But here, they're meant to be much closer, so they have to be much higher resolution. These screens, so this is very different. So basically, you tile them with different pictures of the same thing or different things, so you can just walk around and like say, okay, here it is, and then okay, over there it's different, a different aspect of it. So you don't have to like scroll through things. You can see everything in the same place. You can just move your eyes over to the side and see it quickly, right? And you can talk about it. That's one. The display wall is a very common kind of big thing. Then another thing is CAVE, which is essentially called CAVE, Automatic Virtual Environment. That's what it stands for. And essentially, it's similar to display wall, but it's many display walls tiled around the viewer, right? So there's even a floor and sometimes even a ceiling, and sometimes even closed. So there could be like, it's basically a cube or some rectangle thing. So each of these has basically, there's a projector that projects on each of these. Okay, there's a projector here, and it's projected on this mirror, and then this mirror projects onto this. In this particular configuration, there's many ways to make a cave, but in this case, you have a projector here, projects onto this mirror, and then this mirror projects onto the screen. And then there's also this projector here, projects on this mirror here, and this mirror projects down on the floor. Okay, and that's how it basically. We have built one at Stony Brook about 10 years ago, and it's now at the CVIT, Center of Excellent Wireless and Information Technology. We actually have that there. We don't call it CAVE because CAVE is a patented name, so we call it immersive cabin. Okay, similar concept. There are these projectors here, projector all four sides. We have also a door, so you can actually close it and completely be immersed. And then here's a projector here that projects on this mirror, and then this projects it down on the floor. Okay, so there's a little bit of shadowing when you like stand in front, but but it doesn't really matter that much. But these ones here, there's no shadowing because it's rear projected, right? There's no projector in front between you and the screen. The projector's behind the screen. So what does it look like? Okay, so the inside immersive cabin. So basically, this is a picture taken from the cabin. Okay, so this is very inside a structural molecular bio data set, I think, which is colored by some attribute, and so we can fit quite a few people in this. And you can wear stereo glasses where you can, so now you actually see things in stereo. And it's usually only perfect for the person that wears the tracker, and the other people have to sort of follow along. So it's, but it looks, what the stereo does to you, because you're immersed by the imagery, it essentially immerses you into the object. You don't actually see these corners anymore. You don't rarely see them. And you really feel like you're inside of it. Okay, it's hard to show you when you're not in it, but it's really a very interesting experience. And you can really feel, you can sort of see every little aspect of the data because you can get that sense for the three-dimensional connectivity of the data that you didn't have before. So another one is this. This is more of a building walkthrough. We can see building here. We stand here, so it's a pretty good. You can really have good conversations about the data set. I think there was one building on campus, or more than buildings on campus, where architects actually took their models and projected them into our immersive cabin, and they learned how the building actually would be, how would people behave, how would people feel inside the building that they're architecting. So it would help. And then you could make walkthroughs with the client. And the client then would say, oh, I really don't like this aspect of the building. Can you move this wall a little bit, or can you put the staircase somewhere else? Because it feels better. It makes more functional. So you can really use this for a very good purpose. So here's another one. This is micro-tomography from Brookhaven National Lab, a soil sample. Soil samples on the left, and this is like inside this porous structure. You're actually inside the porous structure. So again, you from outside observer you can see these corners, but once if you wear the headset here, that's shown here, you don't really see this. You really feel like you're really inside this structure. So technology, this is like basically what it looks like. So here's this, it's all projected with a test pattern. There are 5 walls, each of them are 12 by 12. Each of them are 12 wide and 8 feet tall. Makes basically a 12 foot by 12 foot footprint. And so you fit quite a few people. I think that 8 people you can easily fit there. And you have these projectors from fake space. Each of them basically displays an image, and they're interspersed by the one. You have these headsets that they basically project at 60 hertz, right? And then one of them is on and the other one is not. So basically they're slightly different views at a time. So one time you get the left eye view and one time you get the right eye view, but you switch them on very rapidly, and so that way you can actually think it's 3D, because each eyes gets that at the 60 hertz you don't see the difference. So you can basically integrate in your brain. So it's a 3-dimensional picture. So question is, can we get bigger? Okay, the answer is we can, right? So we built this also at Stony Brook University, the largest display of the world in immersive display, which is called the reality deck, because it's like the reality deck, just like the holodeck in Star Wars, Star Trek. It's the reality deck, and there's no floor projection, but it's all around you, and you can see these tiles. Each of these tiles is one display, like one regular monitor. Okay, Samsung monitor, high resolution Samsung monitor, and of course you can fit a lot more people inside of this. And there again is a door that you can close, and sometimes you can use the same data set and just wrap it around, or you can partition it into different aspects, like maybe one group of people looks at one data set, another group of people looks on the left hand side. So there's many different uses that you can have for this. So give you some under the hood, some behind the wall kind of view. So what happened, visualization, it's now much bigger. The cave was 12 by 12. This one is 30 by 40 by 11, right? So 11 foot tall walls, and then the footprint is 30 by 40 feet, right? So it's much larger. It's like that. I've been in this room many times, and it's like really a very large classroom. Like it's not an auditorium, but it's substantial. It's a real room, like 30 by 40 foot, right? And then it has 460 high resolution LCD displays. This was built like in the early. It was built in 2014. In that time, so 6 years ago, these were the highest resolution displays, 2560 by 1400 resolution, and those display ports carbon. That has basically very fast, right? So they're 60 frames per second and have wide viewing angles. They can be viewed from different angles, so they're not like those displays that sort of fade out if you take an angle. If you're not looking straight on, they look good even if you look like from a wide perspective, like 140 degrees or so. And that fueled by a 20-node GPU cluster, which at one point was a pretty powerful cluster when you compared with existing supercomputers. 2 6-core GPUs, 48 gigabit RAM. There are some FirePro GPUs, and hardware synchronization cards to make sure that everything sort of displays at the same time, and 1 terabyte of storage. Okay, and so these are basically, when you add it all up, 416 times the resolution comes down to 1.5 gigapixel, which is there are 6 miles of DisplayPort cables, 6 miles of cables that connect these things in the back all together to the computation hardware. And 240 GPU cores, 2.3 teraflop peak performance, and 20 terabyte distributed memory. So it's distributed because each of them has like memory by itself to store the imagery. And then you really have to pump through this imagery because it's like gets animated, right? It's not just a still image, it gets animated. And I'll show you some pictures. You know, you can actually show time varying phenomena in this 1.5 gigapixel resolution. And 80 GPUs are there. We used AMD GPUs for that. So now there's some pictures from the reality deck itself. So here's the door. You know, the door is actually also monitors, and you close them. It looks just like a, you know, like a display. You cannot see the door. Actually, people get lost because they can't see the full door anymore. But we have a remote control that can open it. Okay, there's always battery in the remote control. Make sure we never get stuck there. So you're really fully enclosed in this, and there we even have a touch table in the middle. You know, there's where you can actually touch it and steer the display. Okay, then we have camera system can track you, so the imagery can change from where you are. We have like this wraparound display that you walk. You can basically walk around the data, and it always gets filled behind your back, so you feel like it's continuous. The data never ends. Right? We have a paper on that, written on that. And this camera is essentially also used to track you, to do gesture control, so things you can drive the resolution of the display, and using the gestures that are detected. So this is the reach of these cameras on the bottom and the top. There's also a sound system, 20.4 channel professional grade sound system. Okay, so you can actually not only see the data, you can also, you know, audially render the data. So you can, if you have like audio connected to the data, you can actually stereo, you know, pump the sound, and you can actually hear the molecules as they open or not, or you can hear the, you know, whatever it is you have, like that goes along with the data. Flowing stream, flowing water and things like this in real time. So you can basically, what this buys you essentially, you know, because you don't have longer just a single monitor, you have many monitors which are all around you. But it helps you essentially, it helps you to make what's called visual query. Okay, when you read, you know, it's like visual query basically is like you don't have to scroll to get to the aspect you want. All you have to do is turn your head. So it goes back to that lecture I gave you on cognition perception, right, where the user has a coarse model in the head, and then the visualization supports that coarse model with more detail. And this is exactly what this appeals to, right? You may have a coarse idea where this molecule was, or where this particular interesting structure was in some data set, but you don't quite know what it looked like. All you have to do is turn your head and look at it, right? Because it's right there in front of you, right? So that's basically called a visual query. So you have a coarse map of things of the world, and then you can look at the visualization to assist you, helping getting you the detail. You know, it's just like in real life. You know, you may not know exactly what your drink looked like, but when you turn your head and look at it, then it's there, right? Or you may not exactly know what this book exactly had inside, but you can just turn your head and read the book, right? Or so you know where the refrigerator is. You just have to open it, and then you can look what's inside. And you know where your whatever you want to get out of it is, right? So just like that, right? So it's like you have a coarse model, and this reality deck supports that by giving you the real detailed imagery. Okay, 2020 visual acuity. So here's the acuity, right? Everywhere here, it's 2020, right? It's like as you see it in real life, you know. So it's like, you know, and then as you go, so you can see as you get closer at 1.5 to 2 foot away. So it's basically arm length, right? So, you know, as you get closer, you can sort of see the pixels, but if you get further away, you don't see them. It looks like real, like the real thing. Like you couldn't get any better if you had more pixels. And that's the whole point of this, right? You know, the resolution of the displays was there, right? You could not get, if you sit an arm length away, even if you had a more high resolution display, you couldn't get more information out of it because your eye can't resolve it. So now you just expand out in a greater domain. You put more of these displays all around you, and then it becomes more like the real world. Okay, so that's why it's called reality deck. So now some pictures from reality deck. So if you step into it, then this is basically, this is a Dubai data set. City, pictures like high gigapixel gigapixel camera, 45 gigapixels of a 180 field of view of Dubai, right? So it's basically half the rail deck is filled by it. The back behind you there's not, right? It's not a surround view, it's just a 180-degree field of view, and so you can, like, wherever you go, you don't have to zoom in, right? It's just there. All you have to do is maybe step up or just look. You can see every detail of this Dubai without doing anything. Just step up and look. This is a Shuttle radar topography mission data set. Again, you see a lot of resolution, basically whatever's in the data. Here's this touchscreen table that I talked about. Terrain modeling, this you can see every detail. You just step up to it, it's right there. Every little airplane, and then you can see. So relief map, sea level simulation. Again, you see very large. You can see very large pictures all at once. Gigapixel imagery comes up a lot nowadays. Taken from outer space or taken with gigapixel cameras, or stitched together, high resolution pictures stitched together into a larger picture. Now you can just see all of these all at once, and you can sort of see small detail, and at the same time you can see greater structures, at the same time, right? So you can, so you don't have to zoom in and out, you can just look at it, right? You can sort of get an overall perception where things are, right? There's Long Island here, right? And then you can sort of go in and look at what is actually there in detail, right? All at the same time. So here are some people looking at this data set, suburban data set. And this is a molecular visualization time where you can, that's actually animated for you. You can sort of see. So that the basals that you see here, that separates the display. So we did experiments in the immersive cabin, like how big, there's a trade-off, right? You can get smaller screens with thinner bezels, or you can get larger screens with larger bezels. And we did like a simulation, like a user study, which kind of, should we rather choose smaller screens but more of them but with smaller bezels, or should we use larger screens, fewer larger screens or displays with which back then had bigger bezels, and we came up with this. So it kind of looks a little bit like, you look out through this lattice, but when you're in it, you don't really realize it that much, that you are in this gridded environment, right? You feel a little bit you're inside a model because you have this lattice around, but it doesn't really disturb you much that there's like this basals around. So maybe a little less scary because this is outside and I'm inside, so you don't get hurt. I don't know if that has any effect on this, but it's pretty impressive. Its update is real time, right? It's a pretty big masterpiece, right? You really, these views get updated in real time. Massive 1.5 gigapixels. It's pretty an engineering masterpiece. Then it's continuous and there's no options at all, right? So let's want to go a little bit into like scientific simulation, like how do people model these kind of things in a visualization, also in a representation. So let's talk about airflow around an airplane wing. When you look at an airplane wing, this usually has this structure here, so it's foil structure, and then where's the flow more interesting, right? If you want to model the flow around an airplane wing, you want to like see how thick do I choose the material, how do I optimize that there's no turbulence or little turbulence that may disrupt the dynamics of it, right? So how do I do this, right? So basically this is what it comes down, is the tip, and then is the flow, right? It goes around here and around here. So basically, where's the flow most interesting, right? Right close to the surface, right? That's where it's most interesting. It doesn't really matter the flow here or down here, right? Most interesting right around where the air meets the matter, right? That's where it's most interesting. That's where you really want to see how does the air behave in this particular area. So what you're going to do is basically create a lattice, a simulation lattice, and later, of course, you visualize it on this lattice. You create this lattice here that is very finely structured around this critical area here. So there's a lot of cells around here, and then it gets coarser as you go further away, right? So you can really see that in detail how the air behaves and what is the temperature and what is the pressure, you know, mapped to ice, mapped to these heat, mapped to these pseudo colors to see like where things are really happening, right? Of course, you know, in the real image you don't see these lattice grid cells, right? In real image you just see the image, okay? But you know, I just show that the lattice on top of it, so you can see like the lattice itself. So basically you go from a regular lattice to irregular lattice, okay? Which this is not actually irregular, this is curvilinear, but you know, it's like a sort of not regular. It's somewhat, you know, not the regular, you know, where it's just square or cubic, right? It's sort of each cell has a different shape, different not shape but different size. And this orient different. So they're getting into this area of grids. So this is the curvilinear grid, basically, you know, structured or called structured grid, where you can actually take this grid and bend it back into a regular grid, right? You just undo the bending, and then you're back into this regular grid, right? Unstructured grid is where you can't bend anymore, right? It's like really just the, you know, cells that are connected in some way that favor the computation, right? So, you know, so here's the, you know, circle around this maybe modeled airflow in a tube. It's another tube, right, or whatever flow, right? And then you basically make the cells go around this tube like this. And there may be some inner tubes here that are also interesting, you know, model that. Right. For example, if you want to like model like a blood vessel, right, you could like, you know, figure out the elasticity of blood vessels. You know, you want to more have a grid like this, an unstructured grid like this. Okay, so this is basically what it looks like if you take what you modeled and map it to color, and then keep the cellular structure. You don't have to keep it, but you can, right? And then you can sort of see where things are. You can see there's really a lot of detail in this area, right, and not so much in others. You know, depending on the resolution, and you choose that resolution to capture every detail where you're interested in, because you don't want to make the same resolution everywhere, right? Because that will be very wasteful. So you want to like focus the high resolution areas where things could get interesting, and have lower resolution areas where things might not be that interesting. Okay, so that's the whole point of this representation, unstructured or structured grid representation. So here's like the BLUNTFIN data set now without. This is the cells, and here's without the cells. You know, so you can really see, right? There's a lot of detail here, and here's just blue, right? Not much happening here, right? So that's why waste so many cells. You do need some cells because there could be low frequency changes, right? But you don't need all those cells because the changes, the dynamics are very low frequency, right? And here it's very high frequency. Lots of things are happening, right? There's very fine differences in the quantity and in the quality of the pressure and of the heat, right? And so here you use this high intensity. So basically this is what scientists work with, right? These kind of grids, like curvilinear or irregular or unstructured. This is what these sort of supercomputers work on, and this is what usually these, you know, even engineers, CAD/CAM engineers often work with these grids, right? So visualization needs to support this kind of grid, right? So the way you do this, basically, there's various methods. I don't want to go too much in detail on these methods, but one of these is basically you can render them by ray casting. Remember we talked about ray casting, volumetric rendering was done with ray casting. You have a set of rays that emerge at the eye point, and they go to the pixels of an image, and go out in the scene. So the only difference really is that you now when you render this, it's no longer going through these cubic voxels, it's going to irregular voxels, right? So now the cubic voxels were easy, right? Because you could organize them very nicely, right? You would know exactly X, Y, and Z. You could index them very nicely, right? Knowing where you were in X, Y, and Z. You could compute what cell you were in. Every cell had the same size. You can easily interpolate them with like trilinear interpolation. Now the cells themselves, knowing where you are in space doesn't help you to figure out the cell in which you are, right? You have to actually traverse a hierarchy of cells or traverse some sort of structure, connectivity structure that tells you where the cells are. you can also do you can also do cell ordering called topological sort, where you know when you are in this cell, then you know where you're going to be next. So you sort of start like, you know, figuring out from where you are now, where you're going to be next as you move the ray from one cell to the next. Also, the interpolation itself is not so easy anymore, right? It's no longer like simple trilinear interpolation because the cell is irregular. So there's more advanced interpolation schemes that you can use. Okay, I'm not going to get into this, but I just want to tell you this. It's basically what's called a mesh of tetrahedral cells, right? So the next thing I want to talk about is and you can then create these sort of three-dimensional, you know, looks. But remember this voxel here, right? It's blue here is not because it's not just an image, right? It's really generated by volume rendering. This light blue phenomena might be behind some other phenomena, right? So it's like volume rendered and composited from front to back. You know, this is like basically, you know, there's no shading. It's just blended together. You just, every time you interpolate, you get a density, you look up the color, and you blend it with what you had before, right? Together with this blending, opacity-based blending that I've talked about before, right? So or you can also X-ray render it if you like. Just add the colors up and average them, but you can also blend them together so you can see which color, which particle is before the other, right? So, you know, and occluded by the stuff in front, right? So, you know, so create these pictures. So same concept that I showed you with last lecture. There's transfer functions, coloring, there's sampling, transfer function, coloring, and then compositing, right? The same steps. So the only thing that's really different is how to interpolate the value from the cell and how to traverse the rays across the irregular mesh. That's the only thing that's different, but same principle in otherwise. So now we're going to go into another phenomena, like, you know, you actually may want to see like what is actually the flow, you know, in this data set, right? What you want to see the vector field. How are actually things moving? You know, if you have like a time varying phenomena, you want to see like where is the flow that you're trying to observe? Like how is the fluid moving, or how is the air flowing through the tube? Right, you want to like see this. So what you need here is what's called flow visualization or vector field visualization. You know, where you want to see the flow behavior, and each cell has a flow, right, a base flow, right, and then looking at all the cells together gives you like a way to appreciate where things are like, you know, moving fast or slow, you know, or where lots of things, you know, you can actually see this by the vector field and where it's moving. So this is like a whole area of visualization called vector field or flow visualization. And if I go to a visualization conference, there's like several sessions just focused on that. Lots of people just work on this kind of area, right? So I give you a little bit some techniques on how this works, okay? So, for example, one way to visualize this flow, one way to just look at the vectors themselves. Yeah, that's okay, right? Called hedgehog or glyph, vector glyph visualization. We just make a glyph or like a little representation for the flow in the cell and replace it by a vector that shows you where it is, and then you look over at this sort of glyph-based representation, you can see what's going on. You know, the problem here is the resolution is low because you can only plot so many vectors, and secondly, you know, it's hard to see 3D because vectors are occluding one another, right? So it's kind of hard to really see how like if you looked at the you know, here it's already hard to see when you look at this cube, right? You don't quite know, you know, where exactly, you know, things are in the third dimension because there is occlusion and there's also distortion and so on, right? It's hard for you to see. Unless you're in a cave, then you can see it in 3D, right? Of course, immersive. But if you look at the screen, it's kind of hard to do. And not everyone has a cave at home. Of course, you can also use a you know, like a virtual headset, right? A virtual reality headset. You know, you can do that too if you like, and people do that. So let's talk a little bit some techniques that people have used to design to visualize flow. One of them is streamlines. So really, all you have to really do is not that easy, but you can. Right, you basically go and try to connect these vectors together. Connect these. So trace this one, and then connect this one, then find out which one to connect next. Sort of create this sort of streamlines, and so this gives you a little bit of an idea how the flow moves. Right, looks like wires, but they're really it's just flow connected. Okay, called tractography, right? You track the individual vectors in each cell and connect them with streamlines, and then you take these streamlines and you use computer graphics to shade them, right? So you can see, you get a little bit of a three-dimensional look, right? So this streamline here, you know, was shaded high because the light source came from here, right? And then here is less diffuse shading, even highlights are shown, right? So it's basically computer graphics. First, to create the streamline, you make micro three-dimensional object out of it, and then you estimate a normal vector, and then you use a light source to apply the illumination model or shading model that we talked about in two lectures ago. And you also map the color to some quantity that you like, for example, temperature. You know, this is a really nice picture, has a lot of insight, like where things go. You can see high temperature flow is moving from left to right. Low temperature flow is going here. You can't see the direction, but you can see, you know, you can see that how it moves, right? And this is engine data, right? So now stream ribbons, essentially, oftentimes flow has a little bit of a, you know, a twisting behavior, right? When this flow is not just a line, right? Oftentimes you can sort of, you know, when you look at these movies sometimes in the desert, like they have this twisting, you know, phenomena, right? Where wind goes through and they twist around. You can sort of see the sand as it moves around, or the plants as they twist in the wind. This is the idea here, right? So basically you connect two streamlines, and always pick the same streamline and create this ribbon out of it. And then you render this as a ribbon. You know, same thing than before, right? You compute the normal vector on the ribbon now and create this set of virtual ribbons and then render them like this, right? You get more of a sense. When you look at it, it's really, you can really see the phenomenon, right? As how it's twisting the air, right, in this particular data set, right? So it's, you know, it's like a stream ribbon visualization. The next is the stream tube. So this is not quite like the stream ribbon, but it also by connecting them in tubes, you can get a little more sense. It's not a ribbon, but you can see a sense. You can get a sense for the directionality of it, right? Because it's now like it's really sort of consistent in a ribbon, right? You connect basically a bunch of streamlines in a tube and see where they go, right? So now, you know, you get a more, you know, sense for the three-dimensional behavior of this flow in this more, you know, you really, you know, because if you had lines that might diverge, but you may not never see this. But now you keep, it's basically a better tracking. You try to keep things that are close together, so you can get a better idea on how things really go, right? So in a bigger picture, right? So this is the stream tube. Then stream surface essentially is these ribbons, but now many ribbons get connected together. So you can sort of see this foil kind of, you know, sweep a line segment basically. It's basically like a very wide ribbon, you know, and then, you know, then you can sort of see how it really folds, right? You can really see how the air or the phenomena folds on one another, right? And you get a better sense out of that, right? You couldn't see this maybe, but you could see this with this kind of representation. So these are different ways to do this, right? These are more static, so these are all static. You can animate them, of course, over time. You know, I don't have a video of this, but you could. Here's another one called stream ball. That's sort of it's kind of like you have this tube, and you know, and then you insert air into the scene, or fluid, or whatever you want to call it. Like, it's kind of like when you're in a river, right, and you pour paint into it, and then you see, you know, some fluid. You pour that into the water, or you drain it. You know, you put some paint into some food coloring in the water, in the basin or something like this, and you can turn the water faucet on. You can see how the food coloring disperses, right? And this is exactly what happens here. You put some paint in this tube, and then you let it advect by the vectors here, right? So it tries to like follow. You know, you can sort of get a little bit of a sense, and you can move that, right? You can move this tube anywhere you like, and you can sort of get an idea how things are, you know, how channeling the flow is, or how dispersive the flow is, but you can get a really good sense for that, right? You know, so you can examine physically based examine the flow field. Okay, so there's another way to do this called stream bell. And then there's techniques. There's like different kinds of techniques that allow you to inspect global structure or local structure. Okay, and I'm going to show you a really cool local way soon enough, like the next slide. For now, these are sort of two techniques that have been very standard and been there for a long time. So hedgehogs essentially are oriented lines that spread over the volume. For example, these are kind of like hedgehoggy kind of looking things, right? You don't really see the direction that well. You just sort of you see the orientation, but you don't see where the direction is. You only see orientation. There's no arrow on it. And glyphs or arrows, they're like icons that actually show you the direction. But the downside of this is, while this is informative, these arrows take room. They take up room, right? So they take up space. So it limits the resolution at which you could show things, right? So you need to, these arrows take up some room, right? So now if there's anything happening inside that arrow that may be interesting, you can't show it, right? There's no small arrow that you can use and you can still see, right? Of course you can print lots of teeny weeny arrows, but the eye couldn't see it, right? You have to zoom in, maybe see it, but once you zoom in, you can't anymore see the overall flow, right? So it's like this, this sort of trade-off, right? Of course, you can go to a reality deck where you can see everything, right? But not everyone has a reality deck at home, right? So you have to deal with this kind of techniques. So there's this trade-off, right? So there's if you want to show directionality, you have to use some sort of indicator, like a glyph arrow or something like what I show here. But that glyph arrow takes up room, which limits the ability, that you can see high resolution detail. You can use hedgehogs, which are tiny spikes, like a hedgehog has, right? The animal has, but then you can't really see direction very well. You can put a little arrow on it, but once you put the arrow, right, you need room, right? And that'll So there's always trade-off. So here is a technique that is sort of has been invented by Brian Cabral, and is actually a good way to show high resolution flow and at the same time get a little bit of an idea, how things are moving, right? In what direction things are moving, which is called line integral convolution. So it's a very cool idea that really has made a sort of revolutionary idea. And essentially it's kind of like a magnet, right? When you think of a magnet, right? You start, you have what you actually bring in is this. You bring in a picture like a flow field like this, and here I show the flow field. Okay, can be much more high resolution, of course, but this is sort of the idea. So you have this flow field, and then you have this picture here. This is salt and pepper noise, just basically random, high resolution, random values, in a picture, right? So this is like this, right? Salt, pepper, and then you try to use this, make this flow field direct these random values here in a way that they can indicate that they follow the flow field. So what you need to do really is just like a magnet. You need to show the field as it directs these individual pixels, right, or connects them together in some ways. And so this is what's done with this kernel, like this kernel here. This is the smoothing kernel. So essentially the smoothing kernel, you follow a flow line like this, connect them like this, like with Topography. Just like before when you created streamlines or stream tubes, you follow them. And then what you do here, at every point here, you basically average those different gray level pixels here. You average them, along this line. So basically just take a finger and just smooth it along this line, right? Just smooth it along this line. So you sort of create this sort of, by averaging it, you create this sort of average gray value that changes, because sometimes you need to have more black pixels, sometimes you have more white pixels in there, changes a little bit, and you create this kind of, picture here. Essentially this is just a circular flow field, or spiraling, could be spiraling or just circular. It's actually just circular, right? And you just went and followed the lines and averaged them, basically convolved them, or basically correlated them together, right? Correlate them together, and then and then you know, create this sort of structure by that, right? Because you only averaged along the line direction. There only those ones are now, you know, connected and correlated together, right? And the other ones are not, right? So you still have randomness along here, but not so much randomness along the line itself. This is another flow field, right? More complicated, you know. So this way, because this is very high resolution, and you can get a lot of resolution, you can get a lot of detail out of that, right? Small nuances of the flow field you can show, of the vector field you can show, just by correlating the random values along the direction of the flow field at a very small scale. Okay. Called line integral convolution, because you integrate along a line and convolve them with a kernel like this, with a smoothing kernel, like a Gaussian kernel. So that's a very good technique to really, this has really had a big impact on the flow field visualization field. So, you know, this was a SIGGRAPH paper, so it had to have some graphics in it to get accepted. So for example, if you have this flower, you know, picture of flowers, right? You can put the flow field around it that goes with the flowers, right? You can create this sort of interesting artistic picture, you know. This is like different flow fields, you know, with the different flow fields on line integrated with this picture here, right? You can sort of get interesting painterly kind of renderings of this you know, regular real picture, right? So it's like, now it's like watercolor that is sort of flowing into one another, but you drive it by this flow field that you impose. Here, Boris Yeltsin, former president of Russia, he's like, basically the hand is like this, but you can sort of, you know, blur it along the direction of the hand as it goes from left to right. You know, this is like, here's like the hand is waving, you know, so before it was not, but here it's waving. It's basically just put a flow field of a moving hand, right? Just a flow field goes from left to right, and integrate the pixels along it, and then you get this motion blur of a hand, right? Very simple. Okay, you can simulate, this is the space shuttle, right? You can simulate, and this is the delta wing, right? You can simulate the pattern of the flow and the heat and pressure on the delta wing. You can like actually now show these fields directly on the object, right? And at a very high resolution, which is very helpful to airplane engineers and so on, right? You can, you know, same thing here, wind the cloud as they move. You can see that too. So line integral convolution is a pretty powerful method. Then texture splats. Texture splats is another way that's sort of similar to, it's a different way to think about things. So what you basically make here, you take these flow icons. Okay, let's say, you know, you want to show a picture just like here, but you don't want to do line integral convolution. You want to like use a different techniques called texture splats. Texture splats. Okay, then you basically render these base pictures, right? So here, this is like a single Gaussian kernel that sort of falls off to the side, and these are these little tiny icons that show you where the flow goes. Okay, so it's just randomly distributed along this textured splat, and they're weakened by the splat function, by the Gaussian function, so they fall off to the sides, right? And here they're most visible, and then to the side they fall off, right? And they have a certain length too. You know, that's also very important. So the length is important, how many of them were there, and the fall off. Okay, so these are important. So you can build a library of this, right? You can say, you know, you can different types of, you know, you can have the ones here that are just very short. They look like the kind of like headlights. They're sort of facing you, and here are the ones that are passed by, and here they're passing by a lot. Right, and here they're blended together with this Gaussian function. So what the key is now, because you blend them together, you're blending them together, you can now put them together like in pictures like this, where each of these is essentially so then you can essentially go through and put them together, like blend them together. Each of these is essentially one of those splats that you showed here, right? That I showed here, one of these splats. Blended together because they're blending together, because one splat is basically comes next, right? They're sort of slowly blending from one splat to the next. That's why they're called splat, because they go like from left to right, and then this creates a sort of assembly that looks continuous but shows different aspects. So this is a splat that has the wind going from left to right, and this is the splat where the wind goes towards the planet, and here's the wind that comes out, right? You know, so you can really sort of quickly see how the pattern is. It has like a 3D appearance, you know, just by graphical rendering with these texture splats. Here's another picture that is here, right? So there's this tornado, you know, that looks like a Mexican hat. You can really see these are like it twirls like this, and here that's coming out, you know, the flow comes out and the flow goes in, right? You can really see how it's sort of, and what the dynamics of this tornado is, right? You know, by it's just different splats, right? These are the splats here that were pointing out, right? These ones, and these were the splats that passing by, right? This, and then they're colored by whatever color you wanna give, right? And you can also give like different intensities for speed, you know, or you can just randomly assign it, right? So you can really get a really good three-dimensional structure of a flow field by a relatively simple graphical technique, right? But just analyzing the local flow, figure out where the vectors are, mapping the right splat to it, and then blending them together, right? You can sort of see this three-dimensional appearance. So the last thing I want to talk about is these libraries. Okay, so if you want to do this yourself, you know, you don't have to write everything by scratch. So remember, we use Python and we use D3 API and all these libraries for your data science projects. In the scientific visualization area, there's also libraries. BTK is a very famous one, called the Visual Toolkit Library, developed by Kitware. And then there's a lot of community effort on this. This is open source, right? So everyone can contribute and add to this library. But Kitware is managing this, a company in New York, upstate New York. ParaView is built on top of VTK, is open source, you know, and then this multi-platform, and this mostly developed by Sandia and Los Alamos National Labs. You know, so it's basically the next step up, right? It's ParaView, it's parallel and ParaView. It basically helps those scientists that work at Sandia and Los Alamos labs to visualize the data they computed, these supercomputers that they have, right? Mostly for defense applications. Visit is another one, open source, developed by Lawrence Livermore, which is another national lab. So these have different capabilities, you know, and a very strong follower group, you know. So this is basically, if you want to do like scientific visualization, you want to maybe look into VTK as a sort of a baseline, because they have a lot of things already developed that allow you to make these support for unstructured grids and support for rendering and so on, right? All of this stuff is already developed, so you can develop higher level applications based on that. Okay, so summary. So we learned today about several things. Right? First, we learned about how to render volumetric data sets as polygonal meshes, right? So we learned about the marching cubes algorithm that we can use to convert those three-dimensional scalar arrays into meshes of polygons. Then we learned about large-scale data. You know, we learned about where they come from, how they were simulated on supercomputers. We learned about collaborative visualization that we can use to display those data sets among a group of scientists, like display wall, cave, Stony Brook reality deck. You know, we learned about this. Then we learned about grids. Like, you know, they're balancing level of detail and representation complexity. So we learned about when you use regular grids are just easy to use, easy to represent, low memory footprint, to curvilinear grids that try to bend a little bit so they can approximate the object where it's more interesting, where it's less interesting, to unstructured grid when the object is already very difficult to represent, right, very unstructured, then you create an unstructured grid for that, right? And then we learned about how to render that briefly. Then we learned about flow and vector field visualization. We learned about streamlines, stream ribbons, stream tubes, stream surfaces, and stream balls. Also learned about line integral convolution, very high resolution visualization of these kinds of data, right? And you can also have some fun with it, you know, look very appealing and so on, right? And then we learned about libraries just now, VTK, ParaView, and Visit. Libraries where lots of these things like streamlines, ribbons, tubes, and curvilinear grids, all of the things already implemented, so you can actually just take the data that you have and create quick visualizations based on that. Okay, so that's basically all I have to say for this lecture. So hope it was informative. If you have any questions, just simply ask them on Piazza, and then the next time around we'll have a streaming lecture where actually we'll have, like, we can have real-time chat and you can just ask questions during the lecture. Okay, thanks a lot.